Hey guys, and welcome to After Hours Academy, where I'm here at 2 a.m. and so are you, so let's just make this easy. And in our last video, we learned how to find a force vector along a line. And in that one, we did know the magnitude of that force, but we just had to find the direction. And this one is going to be a little more of a real-world application. So in this one, we're not going to know any of the magnitudes of any of these forces, and the only thing we do know is that they have to balance each other out. And that's how we get to the idea of equilibrium equations. And I'm going to take a minute to kind of explain the concept of what that is so you really understand it, just because it's something that's going to be really foundational to the rest of your statics course. You're going to be using this pretty much all the time. But if you do want to skip past this more conceptual, theoretical explanation and head straight to the example problem, you're free to do that. I'll leave the timestamp on the screen or in the description. So with that, let me just give a quick little conceptual example. So for an object to be in equilibrium, it means that there is no net force on that object, right? No force is being applied. So that can either mean it's standing completely still or it's moving at a constant speed, not accelerating or decelerating. So picture a little cube, and it is floating through space, right? And no force has been applied to it. It's not been bumped, tapped, anything. So it's going to stand completely still in the middle of space. And that is until you just apply a little bit of force to it in this direction. You just tap it a little bit, and if we're looking at it like a graph, we'll say this is the x direction and this is y. So we're just tapping it a little bit in that x direction, and it's going to start moving, right? So in that moment that force is applied to it, it's no longer in equilibrium, right? Because it's accelerating and force is being applied. But then after a while, it's going to keep moving at that constant speed, even when you're no longer tapping it. No force is being applied. There's no net force. So that also means it's in equilibrium, even though it's moving. It's at a constant speed. So picture this now. Say we still have that cube that's standing completely still, but we applied an upward force in the y direction, and let's say this is a force of 10 newtons. But then say we applied another force at the exact same time downwards, and it's also 10 newtons. These forces have the exact same magnitude and opposite directions. So if we did these at the same time, the cube would just stay still, right? Because these completely cancel each other out. And that is the idea of an equilibrium equation. So the way we would write this out in a statics problem is something like this. We would say the sum of forces in the y direction, and all this means is it's the sum, so all of the forces in the y direction added together are equal to 0, right? And we would write this out like this. So we have this 10 Newton force in downwards in the negative direction, negative y, so we'll say 10 newtons, negative 10 newtons, plus, and this one's going upwards, so plus 10 newtons, equals 0. And this equation is right, it's correct. So say then we have a force applied in the positive x direction. Let's say it's 20 newtons, right? And say we have another force applied in the negative x direction, and let's call this force x. So we don't know what this is, but we can use our equilibrium equations to figure it out, right? So the sum of forces in the x direction is equal to 0. So that would mean positive 20, since it's coming in the positive direction, minus x equals 0. And then we could just figure this right out from here. And boom, we now know what this force is using equilibrium equations. So if that makes sense, then this is pretty much the concept you're going to be using throughout the entire rest of statics. You're just going to be figuring out these missing forces kind of like a puzzle together. So now that we kind of understand this, we can apply it to kind of a real-world example. And in the last video, we did illustrate that with like a hot air balloon example, how you could solve forces, tension forces in cables. So we're going to do kind of the same thing here. Okay, so picture we have a little claw hand, from like one of those crane trucks, and it's pulling up a few cables, just like this. So it's going to be pulling these up, and these are going to be attached to something solid, like the ground, right? So if it's pulling these upwards, that means it's going to be causing a tension force inside these cables. So the force is going to be running through these in the direction of the cables, right? And so well, let's make this into a problem. So we'll label these points, and then we'll just give them random coordinates. Let's just make it easy, and they'll all be 2. You get the idea. Then this one can be, this one can be 4, I guess. Okay. So now we're just going to do exactly what we did in the last one, and we're going to find the unit vectors. So we're going to find the directions of all these different cables, and that's going to give us the directions of all these different forces, if that makes sense. So I'll do the first one, and then I'll skip when I have all of the unit vectors so I don't take up too much of your time. So first, we're going to find the position vectors of all of these. And if you already know what you're doing here, you can just skip forward. So we're going to find this one first, from D to A. So D, my mistake. A is going to have these coordinates, and we're going to subtract D from it. And that is going to give us dA. 2 minus, so all these are going to be -2. So there's going to be our position vector, and then 2, we're going to find our unit vector. And that is going to be all of this divided by the magnitude of this unit vector. And that, I think, I want to say it's 16, but I could be very wrong. I might have to just calculate that. It's not 16. Okay, it's 12 square rooted. I can do math. And all we're going to do is divide -2 by square rooted. So square root of 12. Okay, so all of these are going to be -5.77. And so on. And that is going to be our unit vector, and that's going to be our direction for each of these cables. So I'm going to skip forward until I have all of these unit vectors, and then we'll move on to our next step. So I got all these unit vectors figured out, and somehow I made them all 0.577. I don't know how I did that. I mean, I know how it happened for these two, but I think this one was just a coincidence. I just thought it was kind of funny. But anyways, at least to makes things easier. So here we have all of our unit vectors, which are going to function as our directions for each of these different forces that we're going to have to figure out. So we already have that, and then let's just label these forces. So they're going to be tension forces, so usually they'll be labeled with a T, and then they're going to have their direction, so dA. So we're going to have TDA, TDB, T, it's not very clear, is it? TDC, just like that. And these are all going to be the vectors. So now we get into our equilibrium equations, right? So how we would write out TDA, for example. So for a vector, we need a magnitude and a direction, right? So we should be able to write it like this, TDA, and that's going to be the magnitude of this force. And then the direction, which will be our unit vector EDA, right? 577. So theoretically, that's how we should be able to write it out. And so we should be able to write out all of our different forces that way. So I'll go ahead and do that real quick. And just like that, we have all of our forces written out in terms of a magnitude and a direction. And you may be thinking, how in the world are we supposed to find out these magnitudes? So that's where our equilibrium equations come in. So each of these forces have to cancel each other out somehow, right? because this whole system is going to be in equilibrium. And there's one element that I haven't introduced yet. So you know this claw hand that's kind of pulling up the cables? So in your problems that are like this, there's going to be a force pulling up. And in this example, it was the claw. And that's just going to look exactly like this. And we'll just call that force P. And it is going to be pulling up, and these tension forces are going to be a result of it going down through these cables. So this force that's pulling everything up is actually going to be included in all these equilibrium equations because it is affecting everything else, right? So let's just include it right here. P, and then the direction for this, we'll just say it's straight up, right? So in this graph, we're going to say, let's just say Z is upwards, and then X, and then Y. So it'll be 0, 0, and then it's going to be 1 in the Z direction. And that is going to be P. Or we could write that as the unit vector. So now that we have all this, we can use our equilibrium. So the sum of all the forces in the X direction is equal to 0, right? Well, how we can write that here is we can add all of the forces in the X direction that are listed across these and set them equal to 0. So the X component of this one is here, this one, this one, this one. And all we have to do is add these together. So we're going to say the magnitude times that X component plus this next one. And we're going to add all of these together. And then we could say plus P, but that's just going to be the magnitude times 0, right? And that's going to equal 0. So I guess we don't even need that. So we're going to set it equal to 0. Actually, you know what, for our purposes, I'm just going to add P. And that's going to be our first equilibrium equation. And now we're going to do that for all the rest of these, and I'll go ahead and write those out. And we have all of these equations kind of written out. I know my handwriting's sloppy, but yeah. And just notice this is going to be our forces in X equilibrium equation. The one below that is our Y, and the below that is Z. And these are function the exact same way. They're just this. That's it. So this is this is exactly where we want to get with this problem. And from here, we can solve this just as a system of equations, and we can solve for each of these variables that are going to be the magnitudes of these forces. And you can do that in a few different ways. Like I said, you could solve it as a system of equations, and that's probably how you're expected to. With me, I don't know why, I hate systems of equations. I cannot be bothered to do it. I've never been bothered to do it. I just use linear algebra. And I just input all these things into a matrix and then just figure out all these variables from there. And if you want to stick around, then I can kind of show you how to do that. Not teach you linear algebra, but just kind of teach you how to set up the matrix, how to input it in your calculator and get these values. If you want to learn how to solve systems of equations, I'm sorry, I'm just not the person to ask. Just being honest, I don't do that. Yeah. And one last note with this type of problem. You're going to have to be given one of these little variables, right? So you're going to be given either the magnitude of TDA, TDB, or TDC in whatever example you have. Because if you know about linear algebra or solving systems of equations, you're not going to be able to find all these unless you have at least one of these variables known from the start, unfortunately. So yeah, so our unknowns, I'll go ahead and explain the matrix thing for solving this. And if you are done, if you know how to solve the system of equations, if you have one of these magnitudes known, then that's great. And thank you for watching. So here are going to be our unknowns, right? We need to solve for this one, this one, this one, and this one. And these are our ones we're going to want to find out. So just not teaching you, I'm not teaching you linear algebra from the ground up, just how to set up this matrix. And if you haven't taken it yet, you're going to think, what's this? That's kind of weird looking, but just try to pick up on the patterns here. So ooh, that's not the color I want. I'm going to draw a matrix, and it's just going to have rows and columns of values. And so right here, I'm going to write TDA. And so this is going to be our unknown right here that we're going to want to solve. And these values that are next to TDA, the X, Y, and Z components of it, that's what I'm going to write down going through these columns. And coincidentally, they're all negative 0.577. But if they were different, then you would write the X right here, the Y down here, and the Z at the bottom. And so we're just going to do that for all of these. So T, D, B, and yeah, they're just all going to be the same. I really shouldn't have done that. And then we have T, D, C, and then these are going to be, one of these should be positive. These should be positive. Okay, that's how we can tell the difference. So these are going to be positive 0.577. And lastly, we have, our last unknown is P, and that's going to be 0, 0, 1, as you can see there in the equations. Just like that. And realistically, you don't even need to write all these out. I mean, really, you could just look at the different forces and see what you need to write down, but I wrote this down for clarity. So this is going to be our matrix, right? And you'll notice that each row is basically just a row of these equations. TDA times negative 5.77, TDB times negative blah, 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 P times 0, and then this last part right here is important. It's all equal to 0, right? And so we are actually going to want to include this last part of the equation in the matrix. Set it all equal to 0. And so that's how we're going to want to set everything up. So from here, this just represents an equal sign in linear algebra. So let's just write equals. Here, we're going to input this into our calculator, just the numbers into our calculator, and we're going to, solve it. And the calculator is going to do all the work. You don't need to know any linear algebra for this. So basically just a quick guide on how to do that. I don't have an online calculator or anything, so I'm just going to write down the steps for you on here. So if you know how to get to matrix, so if you have a TI-84, everybody has one, so I'm assuming you do too. So if you have a TI-84, just hit second, and then go to matrix. Right, and let me just make some space here. Go to matrix. And so when you go there, you're going to get, you're going to be in the names column, and you're just going to get a bunch of different options for matrices. So go over to edit. And when you go over there, just pick whichever matrix you want to edit. So you can just do the first one that says A. So just go to A, and then when you get there, it's going to let you pick the dimensions for your matrix. It's going to say 3 times 4, I think, just automatically. So here, you're going to want to say, so if you're looking at it like n times n, then n is going to be this dimension. So there's going to be 3 values here. So you're going to put in 3 times 1, 2, 3, 4, 5, 5, right? Actually, scratch that. You can just input 4. You don't have to put in this column of zeros if you don't want to. You can, You don't have to. So you can just do 3 times 4, or just however many columns have your unknowns in them. Does that make sense? I hope I'm not getting too in the weeds here. Okay. So you can change your dimensions, and then you can just input all these numbers. And it's going to be super easy, just plug and play. Just input all of these. And then you can just hit second and then hit quit. So then you can go back to matrix. So go to matrix again. And then go to math. And then you're going to want to go all the way down. It's a long way down until you can find something that says R ref with a little parentheses. It's not ref, it's just R ref. So if you hit that, it's going to have B beside it, if that helps. B. So if you go to R ref and then go back to matrix, and then select under names, select A, or whatever matrix you edited, and then enter. And you're done. If you hit enter there, you're going to get a finished matrix, right? So I'm going to write down what a solved version of a matrix you get in your calculator might look like. It's not the answer to this because I don't want to input all these numbers right now, so it's not the answer to this problem. But it is just an example of what you might find when you enter this into your calculator. So there's going to be a specific pattern to it that you'll kind of notice. There's going to be ones diagonally right here. And then you're going to get numbers over on the other side, and they're probably going to be negative. So let's just make this all negative 0.311. And it's going to have a bracket. So this is what your solved version is probably going to look like. And if you didn't include this row of zeros, that is. And if you didn't include the row of zeros, when you think about this, you're probably going to want to include it. Because all of this is still set equal to 0, right? Because it's an equilibrium equation. So if we're looking at it like this, then our unknowns are still here, just like in the other one, right? These are all still the same. And so if we let's just make a little space up here. This is probably getting a little bit messy, and my computer is starting to really lag for some reason. So just like hang in there with me. Okay. And I'm also hungry, so sorry about my stomach. So anyway, if we look at this, the way we're going to want to, the way we're going to want to write these equations, wherever a 1 is, whatever unknown a 1 is under, that's going to be the one the rest of this is equal to. Does that make sense? So let me just give an example. So let's write out this first row of this matrix, and you can just see the pattern. So we're going to have TDA, 1 times TDA, minus 0.311 times P. And then there's going to be, let's just picture an equal sign going between all of these, even though there isn't one. It's going to be equal to 0. Does that make sense? Text me. Okay. So this is how we're going to write out all of these. Okay, so if we have all of those, and I did mention before that in these problems you're going to be given the magnitude of at least one of these, right? So let's say it's TDA. Let's say TDA is equal to 20 newtons of force. So if that's going to be our magnitude for that one, then we can rewrite this equation. 20 newtons minus 0.311 P equals 0, right? And here we can just solve for P. Okay. And then 20 divided by 60, let's just say it's 64.3 newtons. So there we have P, and we have one of these unknowns already solved. And what that means is that we can substitute 64.3 into any of these other ones. Right? So you can so easily solve for this now, and this. So basically you just have all of these variables solved for. And so that was my little off the rails ramble on how to use linear algebra on your calculator to solve for these different magnitudes if you don't want to do the system of equations. And again, I'm sorry if that's something you were searching for, because I just do not do that. I cannot force myself to solve systems of equations. I just hate it. It is not fun. So yeah, hope you enjoyed this. Anyone who stayed long enough to see the calculator tutorial thing, I really hope that helped. If it didn't help, then I'm sure there are tons of other tutorials on how to use simple linear algebra concepts like this to solve systems of equations. Yeah, I hope this helped you understand maybe the concept of equilibrium and equilibrium equations, how to solve it to potential example problems you'll have in class, and how to solve systems of equations in a little bit of a more efficient way. And if this helped you, feel free to comment. Listen, if I make some more of these and it helps anyone, then I'll keep making them. I'll probably keep making them either way, but it's fine. And if you have anything else you would like me to explain or help with, then I can do that too. I'm literally just doing this for fun. So if you have anything you'd like help with. Do you see how bad my computer is lagging right now? It is literally... Okay, I think I need to stop recording. I think this is my sign. Okay. With all that said, thank you for watching, and I'll see you in the next one.